Hello, everyone, and welcome to another episode of Vibrations, a TMC podcast. I'm your host, Daniel Litwin, the voice of B2B. And folks, thanks so much for joining us on another episode of the show as we continue to explore the ways that technology is changing, improving, and shrinking in size, and where we, the vibration control experts, are stepping in to support this massive digital transformation that's rocking every industry. Now, before we jump into today's conversation, I want to make sure you're fully caught up on previous episodes of our podcast. So you can find more episodes of Vibrations on Apple Podcasts and Spotify. Just look up Vibrations TMC. You should find our show, give it a subscribe, and you'll find a previous catalog of all of our other conversations we've done in the past. But also, you'll get notified when we drop new episodes of the show. So you don't want to miss our future Vibrations conversations. You can also find more information about our show, more content, including videos, papers, resources, and more information about our solutions and services on our website. So make sure you're also going to techmfg.com. Again, that's tech, T-E-C-H, mfg.com for all your TMC Amatech needs and more Vibrations content. All right, folks, let's go ahead and jump in. We've got quite a bit to cover today, but it's all going to be rather focused. This is a technology-focused conversation. We're honing in on one key piece of the digital transformation puzzle, and that is semiconductors. So today's all about semiconductors. This is a chip podcast. So we're going to be breaking down in more detail the semiconductor industry's latest achievements. And really our goal with the conversation today is to pose up and answer for you guys, how are recent semiconductor breakthroughs influencing various key sectors that are seeing important digital transformations? What are some of the manufacturing challenges of smaller and smaller, but more powerful chips, right? How is the manufacturing side of this also having to evolve to match the use cases? And how critical is vibration control, which we specialize in producing these top quality semiconductors, right? And what role is TMC and Amatech working to play to support these digital transformations and the continuous improvement of semiconductors? We're also going to be looking at some of the steps that semiconductor manufacturers are taking to enhance their efficiency, including electromagnetic interference and reducing said interference, and find new ways to incorporate eco-friendly practices into their manufacturing processes. So we're really going to be looking at the whole pie today. We're going to be digging in and focusing in on the world of chips. So let's go ahead and jump in to the heart of the semiconductor industry right here on Vibrations with our guest. Let's give him a round of applause, Mr. Steve Ryan. He's Divisional VP for TMC Amatech. Steve, great to be chatting again. It's been a hot minute, but it's good to get you back behind the mic here on Vibrations. How you doing today?
Thank you very much, Daniel. Good to talk to you again.
Yeah, absolutely. Always a pleasure getting to pick your brain. I've enjoyed chatting in the past, and I'm excited to, again, hone in on one key part of this larger tech puzzle, but maybe, I think arguably, but maybe the most important, and the one where TMC Amatech has a very important hand in realizing the next phase and evolution of semiconductors and therefore the use cases for said semiconductors. So let's jump right in, Steve. Got a lot of questions for you. First one, though, is that in the last several years, we've seen the semiconductor industry embrace and achieve some remarkable advancements in production quality, production efficiency, manufacturing efficiency, and then obviously also use cases, the possibilities of today's chips. What are some of the recent breakthroughs or trends that you've seen in semiconductor technology that have really caught your attention or given you the most, energy and hype for what's to come? And what are your thoughts on their impacts for various industries? Go ahead and just give us that overview of what you've seen and why it's catching your eye.
Well, what we see is more of what we've been seeing all along. For the many decades that TMC has been in business, working to solve these kinds of problems, going back to the early 1970s, and that is that driven by Moore's law, and that is that each 2 years chip densities double. The patterning keeps getting to finer and finer nodes, and as we move forward, getting down to smaller nodes requires ever more precise lithography and ever more precise inspection and metrology, right, to ensure that the pattern is being correctly manufactured. And what that means is a higher level of sensitivity to all sorts of environmental disturbances. And top of the list is building floor vibration, limiting the ability to meet these advanced nodes, down to sub 5 nanometer, sub 3 nanometer, even 2 nanometer nodes. In addition to floor vibration, there's electromagnetic interference, temperature issues, acoustic noise, drafts, all sorts of other things can and do impact this and need to be controlled. But what we've seen is what used to be a minor nagging nuisance in the early days for TMC become one of the most challenging issues to correct if you want to be able to keep advancing the semiconductor roadmap to the next generations of nodes.
Yeah. And before we get into the manufacturing side of things, I want to talk about some more use cases that I've personally seen really capture my eye. I'm curious if you have any thoughts on them. We've seen semiconductors hone in terms of their applications and use cases. So chips are getting more specific for what role they play in the computing ecosystem. And this is becoming more important as edge computing becomes more prevalent, necessary to realize a lot of the sort of decentralized and digitized goals of smart cities, Industry 4.0, the sort of a autonomous or at least close to autonomous vehicle networks that are being trialed, across various cities. And all of that is, again, reliant on semiconductors that play a complementary role in and chips that play a complementary role in that larger computing ecosystem. So I'm curious, of some of those examples or maybe others that catch your eye, what are some of the consequences, positive or negative, I guess you could say, or at least challenging, that are coming from some of these fast-moving use cases that are requiring more unique and more powerful semiconductors? How's that sort of changing up the whole ecosystem?
Yeah, so what we saw for a long time was the major drivers were microprocessors and memory chips, and there's been a proliferation of all sorts of applications, including automotive applications, military. Now there's AI. No limit to the areas where semiconductors are showing up in the world. Of course, mobile devices, left out mobile devices. We at TMC and our efforts in vibration control, try to understand, well, which of these will have the most demanding requirements for vibration? And that's not really the right question for us, right? Because for us, the manufacturing, it's really a question of the tool sets that are being used to make the patterned wafers and the chips, and the node sizes. So, regardless of whether it's for an automotive application or some sort of aerospace application for a chip, it still needs to be a pattern inspected wafer. And the question to us is, what is the node size? The larger the wafer, typically a 300 millimeter wafer. The question is really then, what is the pattern size? The smaller the pattern, the more sensitive the patterning process and the inspection is going to be to floor vibration and other artifacts. So really, regardless of what the chip application is, it's really for us a matter of what's the node size, and that's going to ultimately limit the sensitivity of the application.
Now, and you just kind of brought this up in your answer, but as semiconductors become smaller, become more powerful, and that form factor just keeps, Moore's law, right, just keeps getting tinier and tinier, what challenges and opportunities also arise in terms of manufacturing, quality control, and reliability of said smaller and smaller semiconductors? Go ahead and unpack that a little bit more for us.
Yeah, so to get to a particular node size, right, requires a number of different tools, each with their own levels of vibration sensitivity and other requirements. But the broad mega trend over the course of decades is that going forward, from the past to now and going forward into the future, the smaller the node size, ultimately the quieter the requirement for the building floor vibrations is, right? So the more advanced nodes need quieter and quieter floors, which means the semiconductor manufacturers have to invest in building techniques to build quieter buildings. And they do. And they've been very, very successful at it. The problem is you can't construct a building to be quieter than the earth that it's resting on. In other words, if you were to go out to a greenfield site and measure the vibration in a field and then construct a building, well, whatever the field was, the building's not going to be quieter. It can only be worse. A building is a set of structures, and structures amplify vibration. They don't isolate them. And what that means is, as you project forward in time, it's just not going to be possible to build any semiconductor factory that meets the most advanced tool set, building floor vibration requirements. And that means you're going to have to do something in the building to make individual point locations where the sensitive tools are located, to make those point locations isolated from the building that they're housed in.
And naturally, right, as the form factor of semiconductors does get smaller and smaller, precision becomes even more important. I mean, it's not like it hasn't always been. Semiconductor manufacturing is known for its precision, but that obviously just gets more acute, and the room for error shrinks along with the size of the semiconductors themselves. So let's start to talk a little bit more about the role of vibration control and isolation in this larger manufacturing ecosystem. How critical is, in your opinion, vibration control and isolation in semiconductor fabrication, and how does it affect the quality of final products? Maybe if you could compare differences, right, where we see this manufacturing in practice without the proper vibration controls and isolations, and how that impacts quality and reliability and QC, et cetera.
Yeah, I mean, ultimately, I think for the semiconductor manufacturers, the biggest issue is one of yield, right? If you've got a vibration problem, it's going to affect the yield and to some extent the throughput. So the vibration sensitive instruments that we're talking about, wafer inspection tools and metrology tools, patterning tools, these tools already have advanced vibration isolation systems built into them. And as the next generations of tools advance, the isolators that are built into these tools get more sophisticated, more complex. There's more performance demanded of them. And it ties back into my previous comment, which is, you get to a point where you still need to isolate the tool. So ultimately you have two levels of vibration isolation. You have some advanced vibration isolation going on built deep into the heart of the tool. And the entire tool then cannot just be sited in a semiconductor fab necessarily without an additional level of mitigation. And the level of mitigation, where the tool is being installed, that vibration isolation system that's going underneath the tool that has another vibration isolation system that demands that the two be inherently compatible and complementary. Right? It would be very easy to stack two complex vibration isolation systems on top of each other and have there be crosstalk or other incompatibility. So it's essential with these advances that the advanced isolation systems in the tool be inherently compatible and complementary with the second stage of isolation that's going between the tool and the floor of the building, or I should say the foundation of the building.
Another disruptive force that gets in the way of quality semiconductor manufacturing is electromagnetic interference. This is top of mind. It's a major concern for semiconductor environments. Could you discuss the importance of mitigating electromagnetic interference in semiconductor processes and why that's so important and how it fits into the larger, vibration control and isolation ecosystem, even if they're not exactly the same, risk to mitigate?
Well, as the semiconductor patterning, as Moore's law advances and the patterning nodes become smaller and smaller, the finer the feature that you're trying to create or inspect or view requires ever shorter wavelength light, right? So it's a principle in physics that to resolve an object, the wavelength of light, that you're using to reflect off it to view through a microscope or whatever, needs to be considerably smaller than the feature size, right? The wavelength of the light needs to be smaller than the thing you're looking at. And so over time, the wavelength of light to do this kind of inspection has become smaller and smaller, getting to the point where it's outside of the visible spectrum. It's ultraviolet, which is not visible, or it's deep ultraviolet or extreme ultraviolet now. We're talking about light. Light is not sensitive to, light is non-magnetic. But as we get to, extreme resolution, that requires something that can be a shorter wavelength than we can practically produce and control with light, and that is electrons. So electrons aren't light, but electrons have an extremely short wavelength, and they're great for imaging very small things, and that's why there are such things as electron microscopes. So when you use an electron microscopes, electrons are charged. They have an electric charge. And that means that they're very sensitive to changes in magnetic fields, background magnetic fields or changing magnetic fields. Not so much the Earth's field, but things that are changing. So something like, the power in the building, electricity flowing through power lines creates a magnetic field that spirals around, that, is coiled around the line. A moving elevator, right? An elevator is going to have some charge that it picks up from static. And a moving elevator means moving charge. You're moving a changing electric field that causes, creates a magnetic field, which is going to disturb an electron microscope. So there are all sorts of, if you were to measure, the magnetic flux density, the magnetic field, if you will, at a point right where you're sitting right now, you're going to see some magnetic field caused by the electricity flowing through the cables in your room, caused by various things, and compound that in a semiconductor factory with all sorts of equipment that has moving stages, and there are lots of sources of things that will create a changing magnetic field. So it's important to be able to control that magnetic field. So these charged electron beam tools, like electron microscopes or other electron beam inspection tools, can perform to their full capabilities. So to do this requires things like measuring magnetic fields in 3 axes, and in response to that, that measurement, you take the signal, you condition it, you amplify it, and you run it back through some Helmholtz coils or pseudo Helmholtz coils. Basically, running electricity through coils is going to create a magnetic field. So we want to sense the magnetic flux density, and then drive a current through those coils to create an equal and opposite field at that point that we're measuring it. And of course, we're doing that in 3 axes all the time. So, that's the reason we're talking about magnetic field cancellation system. The fact that, there's this long-term trend toward using electron beams to inspect rather than optical beams for everything. And also that these magnetic field cancellation systems, again, have to be compatible with the tool, in many cases built into the tool, and compatible with any vibration isolation systems that are being used.
Now, something unique about semiconductor manufacturing and the tools that are key for semiconductor manufacturing is that they have a lot of moving stages, right? And these stages typically need to step and settle very quickly. I'm curious what kind of challenges this presents from a vibration point of view, right? If you had to kind of hone in on just this one unique aspect of semiconductor manufacturing.
It's a big challenge. It's a big challenge because, the tools will have a payload with, as you say, there's a motorized XY stage. So there's some manipulation of the silicon wafer that's being patterned, and, optics to typically inspect that. So this all needs to be isolated from the floor. There needs to be a vibration isolation system built into the tool to isolate this. And the problem is isolation systems, by their nature, tend to be soft springs, mass spring dampers with a soft spring. Softer the spring, the better the isolation. But the softer the spring, the more the payload is going to slosh around as the XY motorized stage moves. As the stage moves, say in the plus X axes and accelerates and gets up to a constant velocity and decelerates to zero, that's going to create a torque and cause the payload to move around on the isolation system. That takes time to settle. So settling time means it takes longer to produce and inspect the patterned wafer, and that's bad, right? You want to be able to manufacture these things at a high rate of speed, which means this motion of the payload, when the isolators deflect and recover in response to stage motion, that needs to be minimized. You want to minimize the moving around, and you want to have the settling time be as short as possible, as close to zero in the time domain as it can be. So that means the isolation systems that are built into these types of advanced semiconductor tools have advanced over the years from, in the early days, being maybe a self-leveling air spring that was terrific at isolating vibration, but not very good at settling the stage motion. So over time, we started doing things like controlling the air in the isolator using electronic valving so that when the payload moved in, again, say the positive X direction, we, prior to even sensing any deflection, we moved some air into one set of isolators and took some air out of other isolators so that would recover prior to deflection. And of course, there's a limit to how well you can do that. And it doesn't really help with the horizontal deflections and horizontal motion settling. So as the years went by, we started using vibration sensors on the payloads, geophones or accelerometers, to sense the vibration of the payload in response to the XY stage moving, and then adding linear motors or voice coils to cancel the motion of the payload in the X, Y, and Z axes. So 6 degrees of freedom, X, Y, and Z axes, pitch, roll, and yaw. And then we started adding to further shorten the settling time and further limit the motion of the payload in response to these stage motions. We started using feed-forward techniques with the motors. So rather than waiting for the payload to deflect in response to the stage, the controllers that are controlling our motors would be talking to the controllers that are controlling the stage motion inside the tool. And when the stage starts to move, we're applying a force before anything is moved. So feed forward of the pneumatics, feed forward of the stage motion control, feedback of the vibration sensed in the payload, feedback of the position that the payload has displaced. So there are multiple control loops trying to limit as much as possible the payload from displacing and get it back to its null position and settled in the shortest possible period of time. And again, that's very complex. And if all that's going on in the tool and you need to then stack it on another level of isolation, you can imagine there might be some crosstalk between those things, and that needs to be planned for in advance to avoid problems.
Now, another side, Steve, of this manufacturing puzzle for semiconductor manufacturers is also helping align the semiconductor slice of the tech ecosystem with some of the larger technology industry and, more broadly, just sort of industrial or manufacturing industry goals of environmental consciousness, sustainability, and action, right? And there's so many different layers to this ESG puzzle, whether it's sort of internalized strategies, whether it's, top-down, requirements that are now being pushed at a state or federal level. But regardless, we're now seeing that semiconductor manufacturers also have to kind of step up and play their part in reducing the larger footprint, carbon footprint, right, of their, manufacturing processes. So I'm curious, with this growing demand for not only semiconductors, but also their end devices, being more energy efficient, more energy conscious and green, how are semiconductor manufacturers addressing some of these needs and maneuvering the challenges that come with a requirement or a desire for more efficient and reliable semiconductor materials, manufacturing, and performance too, to be energy efficient when actually in use. Break that whole ESG sphere down for us. I know it's kind of a lot, but wherever you think there's some good insights to share for our audience.
Yeah, well, certainly one way ties back to one of the first things we talked about, and that is that as time goes on, the next chipsets have smaller and smaller nodes, which means the buildings need to be, semiconductor factories. The front end semiconductor fabs need to be constructed in a way to create a quieter environment, and again, limited by how quiet the ground is that it's being constructed upon. But there are a lot of techniques and structural engineering of buildings to make buildings quiet, and they tend to rely on mass. It tends to be, I'll overly simplify here, but it tends to be, throwing a lot of steel and concrete at the problem, especially concrete. So, to get even a relatively small improvement in the ambient building floor vibration levels in a semiconductor factory requires an enormous amount of concrete, enormous. And concrete, curing of concrete contributes, I think it's about 8% of, global greenhouse gases, CO2 and H2O. So it's about 8% of that. So throwing a lot of concrete at the problem is not very eco-friendly. And so, what we're seeing more and more of is having less ambitious goals for how quiet a building can be constructed. And instead of making the entire building a little bit more quiet by throwing a lot of concrete at it, rather than doing that, focus on the point at which the tools are being installed and trying to create a little quiet island under that tool, if you will. So rather than making the entire building extremely quiet, when you only need it to be at that level of vibration at a few discrete locations, or a few dozen discrete locations, or even a couple of hundred discrete locations, it's better to attack the problem at that point and try to actively sense vibrations at that point, cancel them in a way that you're supporting the tool and create that quiet environment without all this additional concrete and the generation of a lot of greenhouse gases.
All right, Steve, I really appreciate you giving us this overview of sort of a pulse check on the state of the semiconductor industry and some of the challenges and opportunities that are marking this era of semiconductor manufacturing, and obviously their then subsequent use cases. I want to ask a couple more questions here to close things out, but these are a little bit more about TMC Amatech's role in the larger ecosystem. Obviously, we already talked about vibration control, the importance of vibration control in semiconductor manufacturing. But beyond that, we know that collaboration is truly key in the semiconductor sector. Aligning production needs and use cases with the inevitable end use cases for these semiconductors, and sort of playing a chicken and the egg with where's the market headed, how do we adjust our manufacturing and our products themselves to meet that need, and vice versa, is key. And this collaboration extends all the way to collaboration between folks like yourselves, right? TMC Amatech, who play a supportive role in the production process, and the semiconductor manufacturers themselves. So I'm curious if you can shed some light on that, right? And shed light on how you work not only collaboratively internally, because when we talk about TMC, we're talking about TMC working with other Amatech companies, including Precitech and Sterling, to help foster innovation and address some of these common challenges, but also collaborating externally with manufacturers and other partners to elevate the whole industry. Tell us a little bit about that internal and external collaborative force and y'all's role and approach to it.
Yeah, I would say that the way I would put it is the two levels of collaboration that we have with TMC are with the semiconductor equipment manufacturers, right? The people who make the tools that are responsible for the process to create the patterned wafer and inspect it and do all the back end test and assembly and so forth. So there's the collaboration with those vendors but there's also collaboration with the semiconductor factories themselves who are buying those tool sets that in many cases have our isolation systems designed into those tools. And the semiconductor manufacturers then are in the position that they might need to make their building quieter to house those tools, or quieter at certain points with these quiet island, as I had said before, type solutions. So I would say it's two stages of collaboration with the equipment makers to ensure that our things like our new product roadmap are aligned with their long-term plans of where they're going, and we're going to be able to meet the increasing demands of those tools over time for better isolation, faster settling time, less power requirements, you name it. There are all sorts of things that they're going to need going forward. So we're collaborating with the tool manufacturers for the isolators that will be in the next generations of tools, but we're also collaborating with the semiconductor factories to ensure that where they're looking to get in terms of floor vibration levels in the future, without investing great amounts in concrete, or trying to find locations that are quiet enough but impractical. Are we able to deliver? How are we going to deliver the vibration isolation underneath the tools that's adequate going forward? Many years in the future, based on what their roadmap, their technology roadmap looks like.
And then just for a little more clarity here, Steve, for our audience, how does TMC's relationship differ between the end manufacturers of semiconductors versus the tool manufacturers themselves? Because I imagine, those relationships look different, but there's also a lot of similarity and obviously sort of crosstalk with, collaboration between all three parties. But yeah, go ahead and shed some light on the differences there.
Sure. Well, one example would be that, we may collaborate and work with a tool manufacturer for an advanced vibration isolation system that may be, years in the work between the development, the prototype testing, beta units, and so forth. And, when that tool finally goes to market and starts showing up in semiconductor fabs, the fabs very often then approach us and say that, this particular tool is going to be housed in a location that doesn't meet the floor vibration spec of the tool, and they're asking us for help to isolate that tool. Well, we're in an excellent position there, right? Because we know all about that instrument. We know everything we have to know about that instrument in terms of, its mass, its dimensions, internal moving forces, robotic stages, and so forth in that instrument. We know everything about the vibration isolation system built into the tool because we're doing it. So we're in a perfect position then for the fabs, the semiconductor fabs, to say, that tool we're very familiar with, and we have all the information about that tool we need to propose a point of use vibration isolation platform that will, get the floor back into the vibration requirements and yet be inherently compatible with everything about that tool because we're familiar enough with the details of the electromechanics of that instrument.
And sort of to bookmark this then, as we look ahead, I think this, collaboration is going to continue to be key because that's where, not only new opportunities for semiconductors are realized, but that responsiveness to changes that are maybe outside of, even the forces of control of, the TMCs and the tool manufacturers and the semiconductor manufacturers' hands, right? Yeah. I'm curious what you see on the horizon for semiconductor manufacturing based on some of these collaborative conversations you've had with other players in the industry, kind of, where are conversations landing right now? Where do people have their pulse on the market? Whether that's a great opportunity or, somewhat of a rattling challenge. And how is TMC preparing for some of those things on the horizon? What are your thoughts?
Yeah, well, I've been here at TMC since 1986, and I've been watching this play out over more than 35 years now, and seeing the Moore's Law continue to keep up with the predictions. And, I recall even before that, back in undergraduate physics, when we, in solid state physics classes, we're trying to understand how fine pattern you can have before quantum mechanics started breaking down electronics. And, that at the time was seen as the ultimate limit. And it's gotten a little bit more complicated than that. So, here we are now with, chips that have, 2 nanometer node sizes. And, the defects are so small. Just to give you an analogy, so if you're trying to look at a 300 millimeter wafer, about a foot in diameter disk, and you're trying to inspect for a defect over that 300 millimeter disk, the scale of that defect to the disk that you're looking at is within an order of magnitude of a satellite, flying over the Earth and trying to find an ant in Rhode Island, basically. So, we're talking about just extreme levels of, extremely high levels of resolution, if you will. And, having watched it move forward over the last 35 plus years and try to project it into the future, well, we're at the point now where these nodes, are on the order of, several, 5, 10, a dozen, whatever carbon atoms across, so you're almost talking about individual atomic diameter resolution. And frankly, for me, it's hard to project it very much into the future because it's hard for me to believe that, we've gotten to where we are, even though I watched it all along the way. I still find it hard to believe. And I think that's the exciting part to watch how, even what I described is kind of the current level of resolution and, the size of the features. How can you possibly project that forward into the future and, predict where it's going? So I would say it's been just a truly fascinating run and just very exciting to see how it continues to move forward.
Couldn't agree more, Steve. And we'll obviously be keeping a pulse to things and continuing to provide updates here on the podcast of where the industry is headed, exciting opportunities we see on the horizon, maybe some challenges too, and again, how TMC is playing a role to elevate and control some vibrations for the industry. So thank you again, Steve, for your perspectives today. It was really a pleasure. Again, folks, we've been chatting with Steve Ryan. He's a divisional VP for TMC Amatech. And Steve, if folks want to pick your brain a little bit more, maybe read up on some of your other thoughts, where can we point them to? More information on you and your perspectives here.
Oh, absolutely. You can reach out to me through our website. Be the best starting point. techmfg.com, techmfg.com.
All right. Easy enough. Steve Ryan, thank you so much for your time today on Vibrations. It's really been a pleasure, and I'm looking forward to the next episode.
Thank you, Daniel. Pleasure was all mine.
And thank you, everyone, for tuning in to today's episode of Vibrations, a TMC podcast. If you like what you heard and saw today and you want previous episodes, or you want to make sure you don't miss out on future thought-leading conversations here with the TMC team, make sure that you're heading to our website, techmfg.com, and make sure that you're subscribing to the podcast on Apple Podcasts and Spotify. I'm your host, Daniel Litwin, the voice of B2B, and we'll catch you on the next episode of TMC's podcast, Vibrations.